Wait. If we start our module from module section, then first from my portion is, and before starting the syllabus wise, the first portion is consolidation of soil. Now I am presenting one ppt. Just observe. Acha. We all must have wondered by Leaning Tower, Pisa, and you might normally thinking it was designed in a such a way, but real reason, the real reason behind the phenomena which is below the ground, and the soil layer constantly settling due to the load transform from the top by dissipating the excess water pressure. Okay, this getting out from soil layers is called consolidation, which is settlement. So there is lots of confusion. What is settlement? What is actual consolidation? Now we can look. This is again the soil layers constantly settling due to load. Such this is our soil layer, sand, clay, and sand, and this is our load which is coming from the top portion. So some term or one term is now appearing, that is consolidation, and due to some load is there, and normally our material is soil, maybe sand, maybe clay, or maybe composition of sand and clay. So this can be explained with simple diagram. Okay, simple diagram. Soil composed of fine particles, uh, 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 soil particles and voids. These voids are filled with both air and water. During consolidation, the air first goes out. Okay. Now you can see the voids, and these voids filled with air and water. And this is the one diagram where we can see that the during consolidation this air first goes out as soon as load is applied, which is known as compression, and this is followed by the expulsion of water from the soil layer. As the water flows out, the solid particles are rearranged due to age of overall height of soils decreased as such settlement is taking place. Okay, again I am repeating. As the water flows out, the solid particles are rearranged due to a overall due to a age of overall height of soils decreased as such settlement is taking place. My voice is audible to you? Hello? Yes, okay. So this is the phenomena. This is called settlement due to consolidation. Now, also depending upon the void spaces inside the soil, the way they dissipate may vary. Here you can see the particles of sand, clay, and composition of sand, clay, or simply clay. Normally, we are handled two types or two or three types soils like sandy soil, clay soil. Please mute. Please mute. Sandy soils or clay soil. All of you, please request mute. Sandy soil or clay soil or granular soil. Granular soil is the combination of sand and clay where the cohesive soil as well as fine grained soils both are present. For relatively coarse materials like sand, the water reduced first whilst takes the longer time to water to mix through finer particles like clay. Yes, yes. Okay, okay. I'm. Hmm. Okay. Jahir Iqbal, all things are recording. Very careful. Hmm. Yes, sir. अब ठीक है, sir. Okay. I'm starting again. So, uh, for relatively coarse materials like sand, the water reduce fast, whilst take longer time to water to move through finer particles like clay. You can see this in this diagram. The for coarse materials, water reduce fast, and for fine material like clay, this phenomena is taking longer time. Acha. Eventually, this will change the settlement time as well, and also for the for the age of the throughout the age of the time, these phenomena will change and settlements will take place. Let's look at the demonstration. In the same container, one half is the filled with sand in clay, whether other half is just clay. The sample is such a way that they are in water. They are in water. Then a load applied over the sample and taken the consolidation phenomena. After few times, it is seen the half with the sand has settled a little bit more because the poured water has dissipated more from the half. This is known as differential settlement. Okay, and which is not considered can be lead to instability of structures. You can see the structure, and this structure such as the failure of structure such as tilting. This is known as differential settlement, which is not considered can lead instability of structures. The wrong estimates or even negligence of consolidation can lead to severe structure failure. These are the structure failures due to settlement or settlement after settlement, then settlement due to consolidation. First consolidation and then settlement. The Kansai in a national airport is a famous case where the expected settlement was Kansai in Japan. The settlement was 19 to 25 feet, but the actual settlement on one to become 27 feet by the end of island construction, and the end at the continued at the rate of 2 inches per month. 2 inches per month. Another one and structure is can the famous Leaning Tower of Pisa. Through an investigation, the engineers are uh, apparently mixed and layers sand due to age the time for consolidation was overestimated. This consolidation was overestimated, and this after some times the pore water pressure distribution and served different settlement and tilted. Okay. This is the faster pore water distribution below the tower where the sand layer was there. Now if there is a problem, there is a solution, and consolidation is not a exception. Okay, the pore water can be uh, made to dissipate, so the soil is almost fully consolidated before the structure is placed. There are several methods for the dissipation of the pore water, or for to measure this consolidation or this settlement phenomena, like vertical drains, preloading. Here you can see for preloading, some surcharge load has placed on the ground before the construction, and you can see what is happened due to load. The natural water content can easily dissipate due to surcharge load or top load on the ground. Another process is sand drain. Okay, this is used for settlement to protect your structure from the differential settlement or unnatural settlement. Here also some sand drains are constructed to expel out the natural water or excess water from the soil. Here also you can see the process how the water is expelled from the soil. According to Tarjagi, he is Tarjagi. In 1923, uh, according to him, every process involving a decrease in the water content of a saturated soil without replacement of the water by air is called a process of consolidation. And in as per the syllabus, any basic syllabus, we should go through the Tarjagi's theory of one-dimensional consolidation. And for this theory, Tarjagi in 1923 uh, takes some assumptions to simplify the theory, or assumptions for development mathematical statement of the consolidation process. What are these assumptions? The soil is homogeneous and fully wait. The soil is homogeneous and fully saturated. Number 2, the soil particles and water are incompressible. Number 3, the deformation of the soil is due entirely to change in volume. Darcy's law for the velocity of flow of water through soil is perfectly valid. These are very common assumptions. Normally, we are taken for the soil because if we don't consider the soil is homogeneous, then we cannot go for any calculation or because soil is totally non-linear. So, if we consider homogeneous, then only possible to derive mathematical derivation is possible for soil. And soil particles and water are incompressible. The deformation of the soil is due to entirely to change in volume. Darcy's law, because water is present, so Darcy's law is need. So Darcy's law for the velocity of flow of water through the soil is perfectly valid. Coefficient of permeability is constant during consolidation. Coefficient of permeability, I think the coefficient of permeability. And load is applied in one direction only and deformation occurs only in the direction of the load application. That is, the soil is restrained against lateral deformation. Excess pore water drains out only in the vertical direction. The boundary is a free surface offering no resistance to the flow of water from the soil. The change in thickness of the layer during consolidation is insignificant. And number 10, the time lag in consolidation is due entirely to the permeability of soil and thus the secondary consolidation is disregarded. So these 10 assumptions are very important for consolidation. When we are we will go for one dimensional consolidation, Tarjagi has given the idea how we can assume, how we can derive through these assumptions the one-dimensional consolidation for soil. After these assumptions, Tarjagi has gone through some mathematical derivations. This is actually one-dimensional consolidation. Okay, this is actually one-dimensional consolidation. Where you can see the figure I have taken from BC Punmia, and you can see the figure number same as 15.5. The 15.5 figure is on one dimensional consolidation. Acha. Figure 15.5 shows a figure 15.5a shows a clay layer of thickness h. You can see in the figure the thickness is h, capital H, sandwiched between two layers of sand. Okay, two layer of sand is are present, which serves as drainage faces. Okay, when the layer is subjected to a pressure increment, that is delta sigma, excess hydrostatic pressure is set up in the clay layer. Okay, extra hydrostatic pressure is set up in the clay layer, means the present water pressure, the present water in the soil, and the pressure from this present water, that is hydrostatic pressure, is set up in the clay layer. At the time T0, the instant of pressure application, whole of the consolidating pressure delta sigma, that is incremental pressure or stress, is carried by the pore water, so that the initial excess hydrostatic pressure U dash U naught dash is equal to delta sigma, that is incremental pressure. and is represented by a straight line u dash equals to delta sigma on the pressure distribution diagram. That means, again, uh, with time or at the time t0, if the instant of pressure application, whole of the consolidating pressure delta sigma is carried by pore water or neutral pressure, or neutral pressure or pore water is same. Pore water means the pressure generated from the water, present water, which is present in the soil mass, and this carried out by the pore water, so that the initial excess hydrostatic pressure u naught dash is equal to incremental pressure, that is delta sigma, and is represented by a straight line. Okay, is represented by a straight line, that is u dash equals to delta sigma on the pressure distribution diagram. The straight line CED, this straight line is CED, joining the water levels in the piezometric tubes present this distribution. Okay, this CED is the water levels, straight line, and water levels in the piezometric tubes represent this distribution. As water starts escaping into the sand, the excess hydrostatic pressure at the previous boundaries drops to zero and remains so at all times. After a very great time, Tf, the whole of the excess hydrostatic pressure is dissipated, so that U dash equals to 0. Okay. Finally, at Tf time, U dash equals to 0. Initially, it was U dash equals to incremental pressure, that is delta sigma, and at T0, and Tf it is 0, and decrement this decrement totally based on the pore water pressure, because initially the pore water pressure was present in the soil, but after some times this pore water pressure has expelled out from the this soil or clay, because we have provided two drainage layer on the both side of the soil. Acha, this TF at TF time, the zero pore water pressure represented by line AGB. At an intermediate time T, the consolidating pressure delta sigma is partly carried by water and partly by soil, and the following relation is obtained: delta sigma equals to delta sigma dash plus u dash. As you know, this delta sigma is the total pressure, this delta sigma dash is the effective pressure, and this u dash is the pore water pressure. So total pressure is a combination of delta effective pressure and pore water pressure. The distribution of excess hydrostatic pressure U dash at any time t is indicated by the curve AFB. Okay, I think AFB, F is missing. This is F, somewhere F will be there. So AFB, joining water levels in the piezometric tubes. This curve is known as isochrone. This isochrone is not important to us. This is totally fluid mechanics part. And number of such isochrones can be drawn at various time intervals. T1, maybe T1, T2, T3, etc. The slope of isochrones at any point at a given time indicates the rate of change of U with depth. Important. This is important. The slope of isochrones, the name of this curve, isochrones at any point at a given time indicates the rate of change of U, that is pore water pressure, with depth. Okay, simply the relation between time, pore water pressure, and the depth, and the rate of change of pore water pressure. This is we need. So if we start the derivation, what we need? Derivation is not so important because this derivation is just for understanding. Okay, at any times t, the hydraulic head H corresponding to the axis hydrostatic pressure is given by, you can see this equation, H equals to U by gamma W, where gamma W is the unit weight of water and U is the pore water pressure, H is the height, hydraulic height. Hence the hydraulic gradient I is given by, normally I equals to del H to the del J equals to 1 by gamma W into del U dash by del Z. Okay. Thus the rate of change of U dash, that is pore water pressure, along the depth of the layer represents the hydraulic gradient. The velocity with which the excess pore water flows at the depth Z is given by Darcy's law. Okay, so here the Darcy's law is V equals to Ki equals to K by gamma W, again del U dash by del Z, or del U dash to the del Z. The rate of change of velocity along the depth of layer is then given by del V to the del Z equals to K by gamma W del square del U dash to the del Z square. This is only for understanding, so don't worry. Just see what is derived by the Terjagi. Consider a small soil element of size dx dz and of width dy. This is the soil element. The size is dx in the x direction, dy in the y direction, maybe opposite direction, which is not visible because it is two-dimensional figure, and dz, this is the height. If v is the velocity of water at the entry into the elements, the velocity at the exit will be equal to v plus dv to the dz into dz. So if v is the velocity of water at the entry into the elements, the velocity at exit will be equal to, so it depends on the depth. Dz is representing depth. Okay, so now see what has happened in the next part. The quantity of water entering the soil element equals to v dx dy. The quantity of water leaving the soil element v plus dv dz into dz into dx dy. Hence the net quantity of water dq, net quantity squeezed out of the soil element per unit time, is given by delta q equals to dv to the dz dx into dy into dz. Okay, the decrease in volume of soil is equal to the volume of water squeezed out. However, from equation 15.4, I think I have not given this equation, but if we go further in further classes, we'll get this equation, delta v equals to minus mv into v0 into delta sigma dash, that is effective pressure. This is the change of volume changing equation in consolidation will come after some classes or after 1 and 2 classes, where v0 equals to volume of soil element at time t0, that is dx dy dz, and change of volume per unit time is given by del into delta v by dt equals to minus mv dx dy dz del into delta sigma dash to the dt. This is the equation, change of volume per unit time. Okay, equating these two equation v 5 and 7, we get del v to the del z equals to minus mv del into sigma incremental pressure sigma delta sigma dash to the delta t del t, and now this incremental pressure delta sigma equals to delta sigma dash plus u, where delta sigma is constant. So my total stress is always constant, and from this equation del into delta sigma dash by del t equals to minus del u dash to the del t, and hence from equation 8 and equation 9 del v to the del z equals to mv into del u dash to the del t. Okay, combining equation 4 and 10, we get del u dash to the del t equals to k by mv gamma w into del square u dash to the del z square, or del u dash to the del t equals to cv into del square u dash to the del z square. Here new term, that is cv. This is important to us. CB, coefficient of consolidation. You can write what is CB because it is very important. In consolidation, you may ask in any exam. You may ask in your semester exam what is coefficient of consolidation. Any interview, any job related interview, any AE, JE, section engineer, senior section engineer, IES exams, you may ask what is coefficient of consolidation. Coefficient of consolidation is, here just I say the equation, because next classes the what is coefficient of consolidation, what is volume change, what is consolidation index, these parts will be discussed, and you can understand properly. So if anyone asks what is the coefficient of consolidation, only the coefficient of consolidation is CB, and it is K by mv into gamma w. K is the coefficient of permeability and mv is the volume change, gamma w is unit weight of water. Again K into 1 plus E0 to by AV into gamma w. Again one term is there, AV. Acha. Some things I should tell. The equation 15.17 is the basic differential equation of consolidation, which relates the rate of change of excess hydrostatic pressure to the rate of expulsion of excess pore water from a unit volume of soil during the same time interval. The term coefficient of consolidation CV used in the equation is adopted to indicate the combined effects of permeability and compressibility of soil on the rate of volume change. The units of CV are soil on the rate of volume change. The units of CV are centimeter square per second. Okay, so some terminology will come day by day. You should keep your in your mind what are this terminology, why it is used. Okay, so AV is the coefficient of compressibility. CV is the coefficient of consolidation. You can write CV is the coefficient of consolidation and AV is the coefficient of compressibility. But what is coefficient of consolidation and what is coefficient of compressibility, I will tell later after 1 and 2 class. So if you see, this is the basic fundamental of your consolidation. It is visible.
Yes, sir.
Visible, no?
Yes,
So
sir.
this is the basic fundamentals of consolidation. Just for understanding, I have taken this class for understanding. After that, you will get lots of things, basic mechanics actually involved, and numerical questions, mathematics problems. Derivation, most of the cases derivation is not needed to us, because derivation is totally for masters students. Okay, and there are lots of derivations, but for BTech students, in soil mechanics, derivations are not so important. Just for understanding, derivations are just for understanding. You need to understand the phenomena. What is consolidation? What are the terminology are involved in consolidations? Okay, these are the important things. And for you have to prepare yourself for any kind of exams, for job, for any job related exams. Like now the government jobs are available, very number of applications are coming out, so you can apply, and the possibilities are coming. So you should prepare yourself for the your upcoming future exams. For that purpose, all the terminology is important. And what is a phenomenon, this is important, because you may ask what is consolidation. Now then you should be expressed yourself, what is this consolidation, and the all the terminology which are involved in consolidation. So for today it is okay from my side. uh, if you have any question, please tell me. अच्छा, प्रमा, ठीक है, प्रमा। अच्छा, निजाम अंसारी, अनुज कुमार, अंकित सिंह, प्रियंका चौहान, कल्याण मंडल, दिवाकर चक्रवर्ती, जिशु साहा, प्रियंका भारती, मनोज ज्योति साहा, एमडी नजर आलम, अरिजित गोस्वामी, अंकित कुमार, कृष्णु नाग। अच्छा, पायल, देव मारिया, ऋतिक सिंह, अभिषेक विश्वकर्मा, अनुज कुमार, आयन चक्रवर्ती, बुद्धदेव सत्रा, पीयूष मंडल, प्रमाण योगी। Okay, so you can leave. If you have any question, you can. Okay, thank you. No, you may leave. Thank you, sir. Thank you. You may leave. Thank you, sir. Thank you, sir. Stay safe, sir. Thank you, sir. Thank you.